Hello everyone, my name is Ned Dimitrov, and today I'll tell you about designing the Texas Influenza Surveillance Network, and this is joint work with my collaborator Lauren Myers at the University of Texas at Austin and her graduate student Samuel Scarpino. So let me begin by just giving you a little bit of background on the problem. In the summer of 2009, everybody remembers that swine origin influenza came into the world, and one of the first United States that it hit was the state of Texas. And just a few days later, hospitals had to set up these overflow tents outside their emergency rooms to handle the extra capacity of inflow of patients. And so quite naturally, hospitals would like warning before they get an inflow of patients like this, so that they can ahead of time set up their response measures. And specifically for influenza, for predicting the inflow of patients, the CDC set up the Influenza-like-illness network about a decade ago. And what this is a few primary healthcare providers, and what I mean by this is pediatricians, family doctors, that report weekly to the state. And what they report are first the total number of patients that they've seen, and second the patients with influenza-like illness that they've seen. And they typically split this up into 5 age groups as well. For example, ages 0 to 4, 5 to 24, etc. And so just to give you a little bit of an example of what the ILI-net is like, you can go to CDC's website, and the CDC will break down the country into regions like this. And if you go in and you click on the Texas region, you can find a little time series of the percent of visits of influenza-like illness to these primary healthcare providers over time. And so the hope is that this time series will predict the number of people that go to the hospital due to influenza over time as well. The basic problem with the ILI-net is that the CDC mandated the system, but each state is responsible for recruiting their own ILI-net providers, and the CDC didn't give them any guidance on how to do this. And so in 2009, after swine flu hit Texas, the Texas legislature asked the Department of State Health Services 2 important questions. First, does ILI-net work? Does it actually predict hospitalizations? And second, how do we design a better ILI-net? And so in turn, the Texas Department of State Health Services came to us to help them answer these 2 questions. And so when you go to answer these questions, you have to answer several important subproblems. The first subproblem is that there's thousands of possible primary healthcare providers that you could possibly ask to report. But you don't know how those individual providers would behave. So in particular, there's going to be a lot of noise in their provider reports. They might choose to not report at all, or they might report erroneous data. And even if you knew how they would behave, you would have to answer the question of what is the objective function? In other words, what makes one influenza surveillance network better than another? And after we have this objective function that discriminates between one network and another, how do we actually select providers to put into a good network? And after you answer all of these questions, you ultimately have to answer how your answers to these questions compare to existing answers that are already in the literature to this set of questions. And so that's what we'll see in today's talk. To help us answer these questions, the Texas Department of State Health Services gave us the following data. They gave us ILI-net reports, which included the zip code for each provider and the provider's reports over time, and hospital discharge data, which is for each patient that went to a hospital in Texas, some diagnosis codes about why they went to the hospital, and also the patient's home zip code, and of course the date in which they were admitted to the hospital. And so we have about 8 years worth of overlap in this data that we're going to use to design our network. And just to give you an idea of what the data looks like, up in this top chart here is the hospital discharge data, how it looks over time, and on the bottom chart is what the ILI-net reports look like over time. And just visually you can see that there's some agreement between these 2 time series, so there might be some hope in predicting the discharge records from the ILI-net reports. And if you actually do the correlations, you'll find out that there's about a 2-week time lag between them. That gives you the best correlation, which makes a lot of sense in terms of the biology of influenza as a disease. So let's go about answering the first 2 sub-problems, which is how are we going to model these thousands of possible providers and the noise that we might get if we ask them to report into the network. And our basic approach is that we're going to derive provider noise profiles from the existing providers that are already in the network, and we're going to generate mock providers using those noise profiles. So first we have to describe what's the basic model of provider reports. How does a provider report? So here's kind of the basic concept behind the model. Imagine that this square is the population of an entire zip code, and the bottom red part presents the people in that zip code that have influenza-like illness. And the provider basically, ideally, would report the exact same fraction as the people that are actually sick in his zip code. But there's a couple of problems with this. First, we don't actually have data on the fraction of people that have influenza-like illness in the zip code, so we don't know what fraction is the red here. And second, the provider's report actually isn't going to be the same as that fraction. It's going to be a noisy function of that fraction. So let's talk about how to estimate that red part. Well, it turns out that you can estimate the fraction of people with ILI in a zip code using Bayes' theorem. So we know the number of hospitalizations that came from the particular zip code from the hospital discharge data. We know the hospitalization rate from previous studies, and that gives us a distribution on the number of hospitalizations given the number of ILI cases. You can assume a prior and use Bayes' formula to derive a distribution on the number of ILI cases given the number of hospitalizations. And so for that red fraction, what we're going to do is we're just going to use the expectation of that probability distribution. So that gives us a handle on the number of ILI cases in a particular zip code. So let's talk about the noise of the provider reports. When we looked at existing provider reports, we found that there were two salient noise characteristics. First was the report availability, meaning did the provider report at all? And second was the error in the reporting data, which is that if the provider did report, maybe they reported something very noisy. So to model this first part, the report availability, we looked at existing providers and we noticed that their reports were very streaky. So they had a sequence of weeks where they would report, and then a sequence of weeks where they wouldn't report, and then maybe somebody calls them up and reminds them, and then they start reporting again until they forget again, and so forth. And we model that as a Markov chain. So each provider is in one of two states, either a reporting state or a non-reporting state, and they're transitioning between these two states. And you can estimate the transition probabilities from the data. And just to give you an example of what existing providers look like, in this picture on the horizontal axis we have the probability of reporting given that the provider reported the previous week. On the vertical axis we have the probability of reporting given that the provider didn't report the previous week. And so on the top right corner, right here, are excellent providers. So these providers are likely to report regardless of whether they reported the previous week or not. On the bottom right here, are providers that are maybe quite enthusiastic to start. So they start reporting, but then somehow, for some reason, they forget to report. And when they forget to report, they tend not to report for a very long time afterwards. And the providers down here on the bottom left are guys that you talk to on the phone who say that they will report, but then when time comes to actually do it, they never actually do it. So those are providers who are very unlikely to report regardless of what state that they're in. And to model the error in the reporting data, we just use a standard regression noise model because this is quite a standard model and can be estimated from the data. So for this model, there's three constants for the noise. There's C0, C1, and the normal standard deviation, sigma squared here, that can all be estimated from the data. And so that gives us an existing provider noise profile that's made up of the tuple of transition probabilities plus regression constants. And so the basic idea is that we can use that to generate a mock of pool of mock providers. We're going to generate one for each zip code, and we're going to do that by first selecting a uniformly random noise profile from the existing noise profiles from existing providers. And then we're going to generate reports based on that noise profile. And so we're going to generate about 2,000 mock providers, one for each Texas zip code. So let's go on to the second set of subproblems that we have to answer, which is what's the objective function? What makes one network better than another? And what algorithm are we going to use to select providers to include in our network? And our basic approach here is that we're going to use the hospital discharge records to provide us with an objective. and we're going to exploit a submodular objective function to give us an algorithm for selecting providers. So let's take a first try at the objective function. So let G be the goal time series. So this is, for our example here, the statewide hospitalizations, but really it could be any other time series. For example, hospitalizations of at-risk groups like children or pregnant women. Let P be the set of mock providers in our pool. So this is everybody that we could choose from. And S is going to be the subset of providers that we selected. So our first stab at an objective function is just the typical R-squared objective function. So just let me break this down for you here. The right-hand side term is just doing the best multilinear regression from the provider time series that we've selected to the goal time series. And we'd like to see what fraction of the original variance that accounts for. And we'd like that to be as close to 1 as possible. So we're trying to maximize this R-squared. And we're trying to maximize it over subsets of providers. And the nice thing about this is that quite recently in 2008, it was shown that this R-squared objective function is submodular, which gives us some very nice algorithmic properties. But before we can jump in and use it, let's just think a little bit about what would happen if we sample providers just once and go and run this function. Well, if we sample providers just once, some providers are just going to randomly end up having good noise profiles. And those are going to be the ones that are going to be chosen by this optimization. However, in reality, when the state is recruiting providers, they don't know how the provider behaves ahead of time. So we have to be a little bit more careful about the noise model and this optimization. So let's do that. So let C be the noise profile of the entire provider pool. So this is the noise profiles of all 2,000 providers that we've generated. And now the R-squared function depends on C, in particular because the provider time series depend on the noise profiles C. And so our optimization, we're going to try to maximize the expectation of R-squared, where the expectation is taken over all the noise profiles. And one thing I'd like to point out is that this expectation involves many, many terms, exponentially many. That we have about 200 noise profiles and 2,000 providers. So there's about 200 to the 2,000 possibilities for C. And so you're not going to explicitly compute this expectation. You have to sample it to do your optimization. But the nice part is that a convex combination of submodular functions is also submodular. And so this expectation function is also submodular the same way as the original R-squared. Now I'm not going to go into detail about what submodularity is, but I just want to remind you a little bit about what it gives us. The first thing that it gives us is a greedy algorithm for a selection of providers. So the way that this greedy algorithm works is we're going to pick the single best provider, and we're going to permanently add him to the network. And then we're going to look for the next provider that gives us the best increase in network performance. And we're going to add that provider permanently to the network. Then we're going to look for the third one that gives us the best increase, and we're going to add him permanently to the network, so forth until we reach the maximum number of providers that we'd like to include. And submodularity property gives us an optimality guarantee for this algorithm. In particular, it gives us the 1 minus 1 over E approximation guarantee, but it also gives us some posterior optimality gap calculations that we can use to see how far away from optimal we are at most. So let's consider this fifth and most important subproblem, which is how do we actually compare to existing networks and methods for doing the same kind of ILI network creation. So in this graph, on the horizontal axis, we have the number of providers that we've selected to include in the network, and on the vertical axis, we have the R-squared objective function. And we have 3 lines here. The red line is submodular optimization. That's our algorithm that we've been describing. And we have 2 naive strategies. So the first naive strategy is uniform selection by population. So here you pick a uniformly random zip code, weighting zip codes by population. And what this models is an open call for providers, basically saying anybody who wants to report, please come and report, and you're more likely to get providers from more populated zip codes. The second naive strategy is greedy selection by population density. So it's selecting zip codes that have the biggest population density, and what that's modeling is focusing your provider networks on the big city of your state. And you can see that submodular optimization outperforms both of these strategies. So how does submodular optimization compare with an optimal network? So the dashed line here we derive from these submodular properties that give us an optimality gap guarantee. And so you can see that submodular optimization isn't that far from the optimal network that you could construct. And the best or most complex method that's in the literature for designing these networks is a method by Polgreen and al. In 2009. And basically this method is a geographic covering method. In other words, you pick a provider in a particular location and you say that all people that live within a particular radius of that provider, for example 10 miles or 20 miles, are covered. And you'd like to pick your set of providers so that you cover the maximum amount of population. And so here we have two Polgreen methods, one with a 10-mile radius and one with a 20-mile radius. And you can see that submodular optimization outperforms both of these methods as well. But it might be quite difficult to understand what the outperformance of submodular optimization versus the other strategy actually means because of this R-squared objective that's maybe slightly difficult to understand. And so in this picture, what we've done is we've just taken the networks that result from using these methods and used them to predict hospitalizations. And so you see box plots of the errors in predicting hospitalizations. So in the vertical axis here, we have the fraction of total hospitalizations that we are in error. And we have three box plots, one for the Polgreen method, one for the best naive method, and one for submodular optimization. So from these box plots, you can see that submodular optimization has a significant performance advantage over the other two strategies. In particular, 50% of the time, we're within about 10 to 5% error of the total hospitalizations. And this is with a provider network of about 50 providers. But the more important question is, why does submodular optimization outperform those other strategies? And to explain that to you, I have to tell you a little bit about the structure of the population in Texas. So most of the population in Texas lives in what's called the I-35 corridor, which is this north-south corridor that encompasses San Antonio, Austin, and Dallas. And of course, there's the major population center of Houston in the east. But on the west side of Texas, that's mostly ranches, and it's much less populated than the eastern side and the I-35 corridor. So let's see the first 10 locations that are selected by submodular optimization. And for this graphic, we've just removed the noise from the mock providers. So they're giving us non-noisy reports. And one thing I'd like to point out is that with non-noisy reports, the optimization doesn't select very many providers in big cities. So there's only maybe 2 providers that were selected in big cities here. Provider number 4 looks like they're in San Antonio, and provider number 8 who looks like they're in Dallas. But a lot of the rest of the providers are over here in West Texas. That's the lightly populated part of Texas. When we add noise, we see that the selections now concentrate on that more populated part of Texas. That's the eastern part in the I-35 corridor. But again, we don't see many providers in the big cities. In particular, here we see a couple of providers, provider number 1 and provider number 2, that are both in College Station, which you can think of as a reasonably large city that's centrally located between Austin, Dallas, and Houston. But a lot of the rest of the providers are in rural areas. And so that's the major lesson to be learned here, that big cities behave the same when it comes to influenza. Influenza is a very fast-spreading disease, and so if 2 big cities have many travelers going between them, that means that influenza is very quickly going to be transmitted from one of those cities to the other. So in other words, if we have a few providers that are giving us information about San Antonio, I can tell you with a high degree of confidence how Dallas and Houston will behave. And we've confirmed this in other ways, statistical methods besides this optimization. And so that's why you only need a few providers in the big cities, and you can concentrate the rest of your providers in rural areas that are maybe not as well connected to the rest of to the major population centers. But a secondary question that came out of our analysis is that there are a lot of new technologies out there that people try to use to predict influenza hospitalization. So for example, in about 2008, Google created something called Google Flu Trends, which basically tries to predict hospitalizations based on the fraction of search terms that are related to influenza that Google receives from a particular region. And so all of this data is available online. You can go to their website and download it. And so the basic question is, can Google Flu Trends substitute ILINet? What we did was we included Google Flu Trends in our mock provider pool to see if submodular optimization would select it and how it would perform on its own in that objective function. So here, the light blue line represents the R-squared performance of Google Flu Trends just on its own. And so you can see that Google Flu Trends certainly outperforms any single provider that's available in the network. It performs quite well on its own. But the other thing I like to highlight is the dark blue line here, which combines regular providers with Google Flu Trends. And you can see that if we add regular providers to Google Flu Trends, we can increase the performance of the network even further. And so really the best thing to do is to combine new technologies with the old technologies of provider reports to get the best predictions. So I'd like to summarize and conclude here. What we've seen is a discussion of how to design the Texas Influenza-like-illness network, but of course these results are applicable to other geographic regions. They're applicable to other objective functions besides statewide hospitalizations. And we got this intuitive conclusion that at least for influenza, you don't want to over-focus your providers in the big cities. And these results were delivered by the Texas Department of State Health Services, and they were used by them to evaluate and design their network. But I'd also like to conclude with a little bit of a grain of salt, which is that different diseases and objectives could produce different networks using this method. So if you had a disease that's not as fast spreading as influenza, maybe you do actually want to concentrate many of your providers in the big cities. Or if you were trying to predict hospitalizations for a particular at-risk group, you might get a different network than the network that you get for trying to predict statewide hospitalizations overall. Thank you very much for listening.